projectiles in 2 dimensions. Example 1. We calculate the horizontal and vertical velocity components. So ux is equal to 10 and uy is equal to 10 root 3 meters per second. Part A, to work out the maximum height reached. So if we look at the displacement, so sy is equal to 0, we need the value of sy at this point. We're looking at vertical motion. So with suvat taking the upwards direction as positive, because the ball is initially projected upwards vertically. So this is what we're after from here. So initial vertical velocity is 10 root 3 meters per second. The velocity there vertically is 0 at its maximum height, and the acceleration is minus g, because this is the upwards direction and gravity acts downwards against this. We're not interested in time, I've crossed that one out. So from the suvat formulae, the one without t is this, v squared equals u squared plus 2as. We substitute the values in and solve. So the maximum height is 10.3 meters. So you'll see the use of the subscript notation here, but when using the suvat formulae, it's no longer necessary at this stage, but definitely use the subscript notation here to prevent any confusion. To work out the time of flight, so the time the ball spends in the air before hitting the ground here, there are 2 methods. So method 1, looking at vertical motion, and we know that the displacement vertically here is 0, and the displacement right here just before the ball hits the ground is also 0, so 0 meters. We don't need to know the velocity component vertically here, so I've crossed that one out. We're looking for t, the time of flight. So again, suvat formulae, the one without v, s equals ut plus half at squared. Substitute the values in and solve. So the displacement is 0 when t equals 0. We're not interested in this one, discard it. This is the one we're looking for, 3.53 seconds. The ball spends 3.53 seconds going through the air. Again, use the subscript notation here, but it's not necessary at this stage. Method 2. So we know that because the ball falls back onto a level horizontal plane, which is the same as where it took off from, the velocity component here will be the same magnitude as here initially, but it's in the opposite direction. The arrows point in the opposite direction. So when using suvat and taking the upwards direction as positive again, if the initial velocity component vertically was 10 root 3, here it's minus 10 root 3. Remember that velocity is a vector, so this is the vector, magnitude and direction given by the arrow. Magnitude and direction given by the arrow. So on a diagram, it's the arrow that tells you the direction, but when you write the values down and you're solving equations, it's the plus or minus signs that represent the direction of the arrows. Hence this one is negative. This arrow here points in the opposite direction to this one, negative. Suvat formulae, v equals u plus at. We substitute the values in, t equals 3.53 seconds. It's the same value that we got as before, but with fewer calculations. Part C, the range is the distance along here horizontally. So we know that the initial displacement in the x direction, so horizontally, is 0 here. That's where the ball starts. We're looking for the displacement at this point. So for horizontal motion, the ball is going towards the right, so I've taken that direction as positive. We're looking for this value. The initial horizontal velocity, 20 cos 60 from this right angle triangle, simplifies to 10 meters per second, using s equals vt, where s is the value here that we're looking for, and v is 10 meters per second. That's the horizontal component for velocity, which doesn't change anywhere in the motion of the ball. Substituting values in, so the range is 35.3 meters. Part D, to calculate the magnitude and direction of velocity just before the ball hits the ground. So we're at this point, again, because the ball is at the same level horizontally as where it took off from, the vertical magnitude for velocity is the same here and here. The horizontal one doesn't change anyway, that's 10, that's still 10, which means this triangle and this triangle are identical. So the component for the horizontal and vertical velocities are identical. 20 meters per second is the magnitude of the velocity. We can work out its direction by using some simple trigonometry. And because these triangles are identical, the angle here is also 60 degrees. An alternative to work out the magnitude for the velocity is to take the x and y components for velocity and just use a bit of Pythagoras' theorem in this triangle. And likewise theta, which is 60 degrees because it's the same as this triangle here, we could say that tan theta is the opposite, 10 root 3, over the adjacent, which is 10. We could calculate theta that way as well, but in this example these methods are unnecessary. We don't need to do this.